So, I started working on this project for a fun video in May, but I noticed that the Summer of Math Exposition was currently being held. Since I hadn't finished it, I decided to finish making up this LaTeX document and record the video in order to make it for the deadline. I know I haven't posted in over a year, but I have been very busy, and I started my PhD program this January. Hopefully I'll have more time to work on this channel in the coming months, but currently I'm studying for the next qualifying exam. So complex numbers are numbers in R2 with the following form a plus bi, where a and b are real numbers and I squared equals -1. Dual numbers are very similar. They're in R2 with the following form a plus b epsilon, where a and b are real numbers and epsilon squared is 0, not -1. Complex numbers commute, and so do dual numbers. Complex numbers have the multiplicative rule a plus bi times c plus di equals ac minus bd plus ad plus bci. Dual numbers have the multiplicative rule a plus b epsilon times c plus d epsilon equals ac plus ad plus bc epsilon. But what happens if some algebraic structure that includes both the fundamental indicators of both of them? So today we'll find that out. So the matrix forms for complex numbers are isomorphic to AB, -BA, and for dual numbers are isomorphic to AB0A. We will show these here. For A, B, C, and D in real numbers, an A plus BI times C plus DI equals AC minus BD plus AD plus BCI. We should have AB -BA times CD -DC equals AC minus BD, AD plus BC, -AD minus BC, AC minus BD, which by matrix multiplication you can verify is true. Similarly, for A, B, C, and D in real numbers, and A plus B epsilon and times C plus D epsilon equals AC plus B plus D epsilon, which is what we should have. No. That should be AC plus BC plus AD epsilon. So this is a typo. That would be AB0A times CD0C equals AC AD plus BC 0 AC, which again you can verify is true. Again, this is a typo. There should be an A here and a B and a C there. Okay. So putting them together, let's start with just AI times B epsilon. So let's multiply these two different matrices together. We get 0, 0, 0, -AB, which we'll call we know that's AB I epsilon because the real numbers commute, but the i's and the epsilons don't necessarily commute. Similarly, B epsilon times AI is -AB, 0, 0, 0, which we have AB epsilon I. So we obviously see that these are not the same. So AB I epsilon plus AB epsilon I just equals -AB, which we can tell here by them adding up to the matrix for -AB. So let's try this. AB I epsilon times C epsilon, that does equal 0 as we hoped, so the epsilons do cancel into a 0 as we hoped. So we can also verify that. And then AB epsilon I times C epsilon, well that is a little different. That is 0, -ABC, 0, 0, which is equal to ABC epsilon I epsilon from this. But that's the same as -ABC epsilon because that's exactly what the definition of -ABC epsilon is. So we have that epsilon I epsilon equals -epsilon. What about AB I epsilon times CI? Well, we get 0, 0, ABC is 0. We don't have anything for that yet. So really, that would just be ABC epsilon minus ABC I. And we can tell because if we have epsilon, it would be this, and then minus ABCI, you subtract the ABC from this, and subtract negative ABC from here, which gives you positive ABC. So that does equal what we are hoping for. So, and AB epsilon I CI equals negative ABC epsilon. Again, that's what we should get because the i's would cancel to negative 1 for I squared, which is exactly what we do get. So we now know that AB epsilon II is the same as AB epsilon I epsilon. Or yeah, ABC I epsilon I epsilon. So for some reason, epsilon I epsilon and epsilon II both equal negative epsilon. Okay, so and just to verify some of the properties amongst themselves, negative AB times I equals AB I epsilon plus AB epsilon I, again, and then all times I. Again, we're just plugging in this for negative AB, which is what we have here, which to verify this is true, we get AB I epsilon I, which is AB epsilon, and let me just make sure. Oh yeah, no, it's AB epsilon minus ABI. That's what it is. And then we have AB epsilon II is negative AB epsilon. And these cancel out. And this becomes negative ABI, which is exactly what we hoped for. Also, negative AB epsilon is this, again, times epsilon. But this part will go to 0 because it's epsilon times epsilon. And then this part is negative AB epsilon, which again is exactly what we thought. That multiplying by plugging this in for negative AB, we get the property that we found earlier. So, and finally, negative AB epsilon plus negative ABI. Let's do that. Plug it in for there, plug it in for there. Again, that'd be negative AB epsilon plus AB epsilon. And then those are coming from this is 0. This is negative AB epsilon, I believe. And then, yeah, and then negative ABI epsilon I is negative ABI. Let me just look through this. Epsilon I epsilon. Okay. I epsilon I. Oh, okay. Okay. And finally, negative AB times epsilon plus negative AB times I, which again to verify, plugging this in for negative AB and plugging in for negative AB here, we multiply by epsilon, this goes to 0. This actually goes to negative AB epsilon because epsilon I epsilon is negative epsilon. And then AB I epsilon I is AB epsilon minus ABI. And then AB epsilon I is negative AB epsilon, which again, these ones cancel out. And we get negative ABI minus AB epsilon, which is exactly what we started with. So it looks like we found a self-sufficient group of matrices that we can multiply and add by any A, BI, C epsilon, where A, B, and C are real numbers. Now we just need to verify that when multiplying an arbitrary sum of them, we get an R4 vector with special rules, or we can turn it into a 2 by 2 matrix. So we want to show that A plus BI plus C epsilon plus DI epsilon is an R4 vector sufficiently corresponding to the R2 by 2 matrix denoted here, with the current definition we're about to state, and that this matrix will be denoted as A, B plus C, negative B, A minus D, which that will be the definition here. So we're going to run into a few issues with this, but it is going to work for what we need. But I'll show you where the issues come in later. So let A, B, C, D, E, F, G, and H all be real numbers. And let's multiply these out. We get this as the basic, just everything in its rawest form. Simplifying, we get to here. And then regrouping, we get to here to show what exactly the multiplicative rules are for any two R4 vectors, right? And now we just want to verify that these are indeed the same when multiplying the matrices. So again, you can verify this matrix multiplication yourself, which again, if you need to know, it is long ways and then tall ways. I think that's a good way to remember it. Long ways, tall ways. So this is what we get from this. And then we can group everything up so we can see that this is exactly what we need for here. This is what we need for here. This is what we need. Oh, wait, sorry. This is what we need for here. This is what we need for this part, which is here. Again, this is here. And this is the negative D portion of here. And I just want to make sure, yep, everything seems to work out. There might have been a typo somewhere, but I couldn't see it here. Again, this is exactly the same as this. And, oh, here's the typo. Yep, there should be an I here. So this is AF plus BE minus DF I, right? I forgot the I there. That was the issue. Which exactly is what we said the multiplication of the two R4 vectors comes out to. This verifies our attempt at a solution, but there's actually a different way to define the same structure. Because we notice from earlier that I and epsilon do not commute with each other. They commute with themselves, but not with each other. That is an issue, and we'll explain why later. So let's talk about a commutative structure. We may have already noticed that the matrix form is not commutative. Again, matrices are not generally commutative, but you'll notice this has some cool properties, but it's not commutative. So this could cause some issues with using the previous definition to derive a form of complex analytical calculus. If you've done complex analysis, you know that limits involving complex numbers are very important. And limits in calculus can be used by doing infinitesimals. And that is basically what epsilon is. Epsilon is just an algebraic structure version of an infinitesimal. So when we want to expand our horizons to make sure that the structure is commutative, like they would be in a natural calculus setting, we would want to upgrade our matrix definition to R4 by 4 instead of R2 by 2, which in this case, we can do this by doing the tensor product of the R2 by 2 matrices, which define A plus BI and C plus D epsilon respectively. The tensor product of any two matrices is given by the following. So A has 4 components and B has 4 components, all each in 2 by 2 matrices. Then we denote a tensor, this is what that symbol is, B, as basically taking the components of A and putting a matrix B in each of those slots. And you can break that down by turning this 2 by 2 matrix of matrices into a 4 by 4 matrix just by working through it. The B1, B2, everything will have a pattern, right? And if you've never worked on a tensor product before, I'd recommend it. It's very interesting and very useful for quantum computing, which I have made a quantum computing simulator in the past, just for some fun. But yeah, so therefore, if we take this matrix, which we defined, which we showed actually, and then this matrix, we get the tensor product, which is here. This does not guarantee that it is commutative, though, because a tensor B, I don't remember if it's commutative or not. I can't say for sure. So, but a tensor B, we notice that it would be A1, B1, A1, B2, A2, B1, A2, B2. But I don't think it is commutative, because if we did B tensor A, then we would have B1, A1, B1, A2, which that's obviously not the same. So the tensor product is not commutative. So what makes us think this will be commutative? Well, let's find out. So the tensor product of these two matrices is given by the following 4 by 4 matrix. And you can verify that with this definition that we use to get this. Let us have A equals A, B equals 0, C equals 1, and D equals 0. Just plugging in values to see how things work. This would give us any real number. Again, we get A times C is the real number portion, right? So A would give us our real number, which is just the identity row, or the identity diagonal of the matrix. Let us have A equals 0, B equals B, C equals 1, and D equals 0. That gives us our imaginary number BI. Again, because B in this definition has an I component. And again, BI times C, where C is 1, would give us BI. And we plug in those values and we get this matrix. So any imaginary number BI should be in this form. Let's have A equals 1, B and C equals 0, and D equals D. This should give us the infinitesimal portion of the dual number, which seems pretty scarce, but we notice it is exactly plugging those numbers into this definition, because the only places where D and A are combined are here and here. Anywhere else it'll be 0. Okay. Now finally, B times D, we get negative BD and BD here, because we want to say that BD I epsilon is this way. But here's the thing. We have BD I epsilon. That's exactly how we defined it last time with the I first. Let's look at to see if it is commutative by verifying the properties. So let's take BI times D epsilon, which exactly, using our matrix for BI and D epsilon, we do get exactly BDI epsilon, which is what we expected. Again, you can verify this, but this is indeed what we are expecting. But now let's do it the other way. Because the B and the D will commute, the B and the epsilon will commute, so we get BD epsilon I. But we notice that BD epsilon I gives us the exact same matrix as BDI epsilon. So those two commute. The I and the epsilon currently commute when they're by themselves. Let's just kind of look into the entire thing with given any A, B, C, and D. So AB plus BI times C plus D epsilon equals this thing right here. AC plus AD epsilon plus BCI plus BDI epsilon. But let's define A bar, well, let's do B bar, C bar, and D bar such that it is the component of the real number, the I component, the epsilon component, and the I epsilon component of the R4 vector. This will give us A plus BI times C plus D epsilon is A bar plus B bar I plus C bar epsilon plus D bar I epsilon. And we plug this in. And this does indeed give us the exact matrix that we want, which, again, you can plug it in. A bar plus B bar plus C bar. Oh, sorry. A bar plus BI. Let me try that again. A bar plus B bar I plus C bar epsilon plus D bar I epsilon does indeed give us this definition of our matrix now, because this is our original definition, but that's given too many components A, B, C, and D, not in terms of what the vector is, but in terms of what their components being multiplied are, right? Now let's determine if this is exactly what we want it to be by doing exactly what we did before, which again, this is exactly what we got before. And now let's go. Well, actually, I believe this might be slightly different because they do commute. So this is a slightly different number because they do commute. Let's just look back. Yes, it is very different actually. But because they commute, looking at everything, there's going to be better simplifications, right? Everything is going to simplify much, much easier. Because some things that have two epsilons in them are going to turn into zero. And by two epsilons, I mean an epsilon squared because they do commute. And I squareds are going to cancel to negative immediately. So, well, really that wasn't an issue before. But if it was, it could have been if it was I epsilon I, which would have been like some weird number before. But let's focus on it here where it just ends up being the negative, right? So this thing is the raw data like we had before, but I did do extra commuting this time. Then plugging in all of the values for everything, we get this. Which again, grouping everything, we then get this. I'll leave you to verify that as well. Because really, my goal is to introduce this to you guys, not to go over every single detail. Because the details are all here, you can look at them, but it's tedious and you really don't want to listen to me say it all. I mean, I'm going to make more mistakes just talking, so I'd rather you look at it and verify it yourself. That gives you a little exercise, and it gets you introduced into this topic of complex dual numbers, which I feel like I might have invented, but I'm not sure. So again, let's do exactly what we want. Check if everything commutes, which, oh wait, here we go. This does actually give us the vector we were originally hoping for. Now, I'm not going to actually check if it commutes because I did all the steps here. Basically, to do the steps in the opposite direction is the exact same thing, just every single order of, like, it would be EA instead of AE and so forth. Everything would be flipped. It would be the exact same thing it would just be very tedious to change all of these symbols in different orders because there's so many different combinations. So I'm actually going to leave this as an exercise to the reader, not because it's difficult, but because it's tedious and I've already done the first case for you and you can verify that they are indeed the same. Now, looking at a conclusion, we talked about a few different ways to define very similar structures, but they have completely different properties. So maybe there's multiple ways to do certain things, right? In math, it's not always about what can be done with a certain thing. It's how can you define something so it can be done, right? It's not can something be done. It's how can you define something to get it done, right? And so if we're looking for certain properties, then it may be advantageous to use the more strict way. But if you want like the basest, most simplified rules in multiplication, then you will actually just force yourself to discover the new properties, right? Because if you're restricting it to have certain properties, it's going to be much more difficult to figure it out what the structure should look like. Maybe. I don't know. But for actual discovering the properties yourself, that just sounds like a fun exercise if I were you. You know, that's what the first whole part was about, right? So you see the matrix form of what we made. I'm pretty sure this is, where is it? I'm pretty sure that this is just so interesting to look at the features of them not commuting. I find non-commutative algebras pretty interesting, but that's just me. But then, here, think about it like this. A lot of first-year calculus courses don't touch on complex numbers, even though most people learn about them in their second high school algebra course, right? With the quadratic formula. However, the study of calculus is really just the study of limits and how that creates new operations such as differentiation and integration. I personally don't know the exact methods that would be used to give infinitesimals like epsilon a place in calculus because they are very algebraic and exact rather than limits. But there exists something similar called the hyperreal numbers, which has infinitesimals and numbers larger than infinity, which I'm sure you could probably expand the dual numbers to some sort of version of similar to the hyperreal numbers, because I don't know how you would divide, or even if there would be inverse elements, or I don't know, because it is a zero divisor, epsilon. It's a non-zero zero divisor. But the thing is that that's not restricting it to not having inverse elements. I personally don't know how that would work. I could do more details on it. I could look into it, make another video if you guys would like. But overall, this is just a lot, you know? It's a lot of learning because I'm doing this all from scratch, you know? And I'm trying to figure it out for you guys. So if we look at the complex dual numbers, which are a structure of R4, then we have two different ways to define them, one being commutative and one not. So it may be clear to think about it as a non-commutative number system. Well, because first off, some people may know that the quaternions are an R4 generalization of the complex numbers, which are not commutative themselves. But also, you may think, okay, well, it makes sense to not be commutative because all we're doing is matrix multiplication. We're not doing a tensor product, which is, you know, but there's nothing about the tensor product that makes it any less valid. It's just not used very often in like lower level college classes, right? And so, but it may be clear to you to think of the complex dual numbers as a commutative structure, because why would we use it if not for the analysis of limits, right? So thinking about it, realistically, it depends on your use case, right? There's always new things to think about in math. As far as I know, I am the first person to discover this, right? I could be wrong, but it's not really about the discovery itself because it's not going to always be groundbreaking. This probably isn't groundbreaking. It's just putting things together, right? But if nobody's ever done it before, that's pretty cool, right? And the analogy I use is that no matter how many people are making however many calculations, there will always be a bigger number that nobody has ever thought of. That doesn't mean that it's super interesting, right? You can think of that number first, or you can use it just like you could use a new mathematical idea or item, which is possible with enough creativity or effort for pretty much anyone who has a decent background in math. Like, I mean, you pretty much need to create some sort of new reasoning for math to get your PhD, which is what I'm doing. And it has to be substantial enough to make a thesis on, as far as I know. But that doesn't mean it's out of anyone's reach, because it could be as simple as, hey, this number has never been used before. Not obviously for PhD, but like overall, you know? So this has actually been my first submission to the Summer of Math Exposition. I'm not going to edit this video. I'm just going to have you guys hear my raw audio. I don't really have time. I slacked. I don't know. But I hope you guys enjoyed this video. It's kind of me just rambling on about this. But I came up with this as far as I know, and I find it very, very interesting. And it's taken me a while to actually figure stuff out. I mean, I started it way before May, and then I couldn't figure it out, so I just scrapped it, and then I came back to it, you know? But overall, I hope you guys enjoyed this video, and if you did, or even if you didn't, you can check out my other videos. They have a few views. People seem to like them. One of the biggest ones is Wolfram Alpha Can't Solve This Crazy Integral. That's a very popular one. And then on top of that, I also have my very first video, which is why I created my YouTube channel, because I came up with a pretty new proof, as far as I know, to solving a certain sum, which is the sum, well, some version of the sum, the nth Fibonacci number over the nth power of 2, all summed from 0 to infinity, which I find that very interesting. So, but thank you so much for watching this video, and I really hope that you guys enjoyed. You know, it is a very, very long video. I'm not going to cut this down. I know it's a lot of exposition, a lot of talking, but that's what the Summer of Math Exposition is, right? So, thank you so much. Bye-bye.